Hi, everyone, and welcome to Zymposium. I think hopefully maybe this will not be as long as our last symposium, but we'll still have a good time together. I thought what might be fun for this one would be, we did the updated ZIO2 version of our ZIO From Scratch series a couple months back, and I think one thing we talked about doing there is implementing some basic concurrent data structures with that. And I thought that could be a fun thing for us to do today. So I thought we'd implement ref and promise. I think we'll see ref's going to be pretty straightforward. Promise will also be straightforward, but will require like a little more thought. And I think they're kind of fun to like see how there's not any magic in how those are implemented and how some of the tools that we've got with ZIO can make it pretty easy for us to do things that seem like they might be hard. So that's going to be my plan for today. As always, I'll be trying to check in on the Discord as we go. But if I don't pick it up right away, I'll swing back there. So please post your comments there, and I'll also just grab the link and I'll post that. 1 second. Okay, so I just pasted the Discord link in the Zoom chat. If you have a question or comment, the Discord is the best place just because it will exist after this Zoom session ends. So if people have follow-ups or we'll have further discussion, it'll kind of live there. All right, so let me share my screen. And I'll make this a little bit bigger. So it's been a little while, but here's where we left off with our ZIO from Scratch work. So we implemented ZIO. We had the trait, we had the companion object. We had this idea of what a fiber is. We had a runtime fiber that was actually running. And we had all sorts of fancy low-level logic here to make that work. And then we had a couple other kind of simple versions of ZIO data types like exit, pause, some runtime flags. And if we go back up to, I think here, we have a little summary of what we did. And so we implemented this nano actor-based runtime that's more similar to the ZIO2 version. We implemented forking. We introduced typed error channel as well as cause, so we can capture interruptions. And then we got to the concept of interruptions. We got the interruptibility, and we even got the finalizers. I don't think we implemented fiber refs ourselves here, but we saw working with them last time. So maybe if we want to, we can do another session where we like implement our own version of fiber refs here. But I think I'm gonna get started, just maybe do a little bit of cleanup here, just because we got everything in one giant file. And well, we did all this from scratch, and it was I think it was actually pretty straightforward at the time. We did it over a couple sessions, so we got like 800 lines of code here. So let's maybe try to make this a little more manageable, just if we're going to keep building stuff here. And I think also we had that little XIO versus ZIO thing because we were trying to avoid the namespace until we got that. So I think maybe I'll just fix that, move that over there. And then let's just create a couple of new, let's do like a ZIO.scala in here. So I can take maybe everything ZIO. It's all ZIO down to, I think, here. I think this is the ZIO companion object. So I'm going to grab all this stuff. And I'm going to bring it into here. Hopefully that'll be happy. Let's say, I was in the tail right here. Okay. Okay. So let's use the tail right here. Maybe I wasn't. Okay. And then I've got this fiber thing. So let me make example for that. And got the interface for the fiber. Okay, then we have a fiber runtime. Which is this whole big guy here. So I'm gonna grab all this. And, okay, this was also tailback. Okay. And we have a fiber message. Exit. And we have cause. Let's do. Okay, we have some runtime flags. And it's like I had a runtime flag. So let's see runtime flags. Oh, we did do fiber off. Look at me, not giving us credit for all. Yeah, fiber off. Boy, this is starting to look a lot like ZIO, right? And now this is really just going to be example. So I can just rename this. All right, that's I think a little more sane. I'm just going to quickly switch over here and just make sure. Okay, seems like we don't have any questions, which is awesome. Okay, so I think then our goals are going to be to make this feel even more a little real. And so we're going to try to implement a ref here. And we're going to try to implement a promise here. And so we'll do the ref first. And so the ref, for folks who've worked with it in ZIO, is the ZIO equivalent of a Java atomic reference. And so this is really useful if you need to communicate information between different fibers. So you could imagine if you have like 10 fibers that are each doing pieces of like some kind of work, and you want to say, well, when all the work's done, we want to do something else, each one of those fibers could decrement a ref. And if they were the last ones to decrement the ref, then they would go on and do something else. And so the ref is going to be like it's going to have a pretty similar interface to a atomic reference if you're used to that, but everything's going to be wrapped up in a ZIO. So, and let me just look at our ZIO here. I think our ZIO here only has 2 type parameters, if I'm remembering correctly. Yeah, we never did the environment type, so that could be another thing for us, but we won't need it here. So one thing we can do with these refs is we could just get the value of it. Another thing we're going to be able to need to do is set the value of it. And then we're going to have a whole bunch of operations that are going to let us update the ref atomically. So these two operations are, if we just combine them separately, they're not going to be atomic, but we're going to have our own variants that are going to let us do them atomically. So if you've ever worked with like a atomic reference, you probably remember there's like update and get versus get and update. And there are even the lower level ones of like compare and set and things like that. But in ZIO, the most fundamental of these operators is this one that we call modify. And so this thing, you give it a function that gets to look at the old state and gets to update the state. So it gets to change the state potentially. And then it also gets to return a new value based on the state there. And what we'll find is if we can implement this, we can implement pretty much all the other operators that we're used to. And if we want to have like the update and get or get an update, or we just want to update, all of those can kind of be viewed as more specialized variants of this. So this is kind of the really important one for us to get right. And the reason that we need these, and maybe we can show this once we implement it, but if we don't use this operator that does the updating at once, and we just get and set, there's the potential that if different fibers are interacting with the same ref, one of them can make a change that clobbers the other, and those updates can get interleaved with each other, and that can create errors in our program logic. So if we're ever updating a ref, we want to use one of this modify or one of the operators based on it versus separately getting and setting. So this is the interface that we're going to want to create. Again, please feel free to jump in at any time if what I'm saying isn't making sense, or if I'm kind of jumping ahead too much on kind of why we need this. But in the absence of comments, I will keep going here. Okay, so this seems like a reasonable interface. And so the question could be, how are we going to implement it? And what we're going to find is that the ref is really, in a way, it's you could say it's a very light wrapper around a Java atomic reference. So we're actually going to use the Java atomic reference in our implementation of this ref. And we kind of have to do that, because if we want these operations to be atomic, we need essentially kind of the bare metal support for that comes from Java, and then Java kind of does it on top of these like very like low level like primitives that like are at like the machine level of these different architectures. So we really, one, we just don't have any other way to do it. And two, it's already there for us, so it makes our lives relatively easy. And so what the ref really then brings to the table, in a way, is not a different functionality than the atomic reference gives us, but it just lets us work with these atomic values in a ZIO idiomatic way. So all of these things return ZIOs instead of returning just doing these things. They're all descriptions instead of doing things. And it also just gives us a little higher level operators. So like this modify ends up being much nicer to work with than the Java API, I find. A lot of times you'll be able to express things with kind of one idea with modify, versus if you were just using the Java primitives, you kind of need two steps to say what you want to do. And maybe we'll have a chance to look at an example of that. And then the other nice thing about this is it's just available on a cross-platform basis. So if you're ever working with like Scala.js, you don't really need the power of a ref this way, because Scala.js is just single-threaded, so you don't actually need to worry about like having conflicting modifications. But a lot of times, if you're writing library code or you're writing internal library code, you want to be able to support different platforms. And if you work directly with the Java primitives, like the atomic reference, you can run into this problem that like some of the operators don't exist on Scala.js. So then you kind of need to shim them yourselves, or you need to have more platform-specific files, which is not any fun. Okay, so let's go and let's start implementing this here. So the way we're going to create one of these things is we'll have a method that we'll call make. And so this is just going to take an initial value, and it's going to give us a ZIO with a ref inside. And so we're going to do this in terms of a Java atomic reference. So we're going to create one of them. And the first thing I'm actually going to do here is I'm going to use our ZIO succeed, just to create a block here where I can do things and to make sure this whole thing is going to be a description. And I'm just going to go here and I'm just going to verify a second with our constructor. Yep, let's see, we did this as a by name parameter. So this is just going to describe whatever synchronous block of code we're doing in here. It's not going to actually do anything until we run this ZIO. Sorry, back to our ref here. And so the first thing I'm going to do is I'm going to make one of these refs, and maybe to, so I'll do val ref is equal to java.till.concurrent.atomic.reference with this initial value. And then I'm just going to basically implement this ref in terms of it. So I could just do a new ref of A. And then I need to implement these methods here. So how do I go about doing these? Well, I can, at least for these first two, I can do them pretty easily just in terms of the interface of ref. So this could just be ZIO.succeed ref.get. And this can just be ZIO.succeed ref.setA. And this is kind of a nice example of like a pretty basic but kind of useful pattern of if you're working with something that you want to kind of create a ZIO idiomatic interface for, the like easiest first step is just take the existing interface and wrap all the methods in ZIO. So you could say, okay, here, this ref thing has a bunch of complicated logic internally built into it. We want to use it in ZIO. We're just going to take all its methods and we're going to throw ZIO succeed around them. And that is not a bad place to get started either for this, or if you're working with some more complicated interface that's doing some kind of database access or some other type of interaction with external systems. So the one that is going to require a little bit more work here is this ZIO.modify operator. And the reason it's just going to require a little more work is that there's not a one-to-one correspondence between this method and the ones on ref, because this is a little bit of a higher level method, you could say. It kind of combines a little bit of like a update and get, but then it also lets you like change the thing that you're getting. So it's not actually just the value, but it's this other value you're producing. So we're going to have to implement this ourselves. And it'll be a nice opportunity, maybe a little bit, to see the lower level operators on this ref here. And so what we're going to do is we're essentially going to implement this in terms of a loop. And so what we're going to do in this loop is we're going to get the original value of A, and then we're going to try to set it to this new value. And we're going to take advantage of this compare and set operator that this atomic reference provides, which is basically going to set the value to the new value as long as no one else has changed it from underneath us. But if someone has changed it from underneath us, then it's just going to return false. It's going to tell us like, hey, we weren't able to change it. And then we're just going to repeat the whole thing over again. We're going to say, oh, okay, someone else made a conflicting update between us getting the value and setting the value. So we're just going to do this again, and we're just going to get the latest value that reflects whatever changes this other person made, and then we're just going to do it again. And so that's basically going to be our logic here. So let's kind of walk through this. So we could say val old value is equal to ref.get. So this is going to give us an A. And then we could say, yeah, we can give this whatever name we want. We could call this summary, and new value is equal to call this f of the old value. And then, so we got the summary, we've got a new value. So then we're going to say loop equals not ref.compare and set old value, new value. And so this maybe is a little bit, just requires like a little bit of thinking because we have like the negation here. But this compare and set is going to return true if we succeeded. So if no one changed this from under us, and it's going to return false if someone did change it from under us. And so if we succeeded, if no one changed it, then this will be true. We'll negate it, so this will be false. So we'll set loop to false, and we'll break out of the loop, and we'll be done. Versus if someone did change it from under us, then this thing will be false. This will set it to true. Loop will be true. We'll just repeat the whole thing over again. And then the only thing that we need here is we just need a way to get this summary value outside of the loop here. So I mean, because it's a loop, there's not necessarily any particularly, we actually need to get both these values outside. So maybe we can, let's see, I think we can, let's see if we can do this as an assignment. We have to do separate. So we could say bar summary is going to start off with being null. Bar new value is going to start off being null. And so I'm not sure if I can do this structuring this way, but we'll find out. Yeah, that's not too happy. So why don't I call this? I'm just going to do a little ugly. I'll just call these 0. Maybe I'll just do val tuple. And then I can just do so tuple 1, the value is that. And then I can finally just return the summary and the new value. And let's see. Oh, right. I actually don't even need to do that. I don't know why I was being silly there, but I don't really need that. So do that. And okay. Now there's a question from Naveed here of should we do succeed blocking here? And the answer is no, we actually don't want to do succeed blocking here. And the reason is we expect this to complete extremely quickly. And there's no circumstance here where we're really spinning because most of the time, right? This F operation should be very fast. It's not doing any kind of workflow. At least if someone is doing a sane thing with this, this is like updating a value. So in all likelihood, this is going to succeed the first time. If someone else clobbers us, then maybe we're going to have to go one or two more iterations, but it's definitely not something that we expect to take long enough where it makes sense to shift it to a separate thread pool for this. And that would also just have a really negative impact on our performance if we had to do that for every one of these loops here. Okay, perfect. Okay, so that already gets us kind of most of the way there. And really from here, I think the only thing to do is we can maybe implement a couple of other convenience operators that are simpler variations of this modify method. And then maybe we can do like an example or two just to see how this works. But this one's pretty straightforward. So we're, I think, pretty close to being able to declare victory here. But let's create a couple of these simpler variations. So we might say, hey, I just want to update it without having to, like, I'm not interested in any summary value. I just want to update this value. And turns out this is pretty easy to do because we can just say, well, modify, and this will just be unit. So this will just take the value and it'll just return unit and after the value, and another parentheses there. So that's very easy to implement there. And I could just, I wanted to make that final. So I say, okay, as long as I can implement modify, I can implement that. And then we have some variants of that. We have like update and get, right? That's probably one we're used to if we've worked with the Java versions. And so here, so update and get. So this means that this is going to return the new version. So maybe just so I only call this F thing once. Should be a pure function. It should be okay to call it more than once, but just maybe for efficiency or just to be sure. Let me just, I'll give myself a here, and maybe I'll call this old value just for clarity. And so I could say val new value is equal to F of old value. And then I can just return a tuple. I'll both set it to the new value and I'll return the new value here. And then we could also do it the other way. So I could do get an update. And so I could say, okay, well, we're going to compute the new value, and then I'll set it the new value, but I'll return the old value. And so let's see if we can do an example here. So maybe I'll create another file here, just try to keep myself somewhat organized. I'll call this ref example.scala. And let me look at how I was running these things just to remind myself of, since this is not the actual ZIO, I need to, okay, so I think we had an unsafe run sync. Okay, perfect. Okay, so let's do object example extends app. And why don't we do something like, let's say, val ref example. And so this will just be a ZIO can't fail. It doesn't return any useful information. And I'm going to say for ref, and ref.make 0. And then let me just look here for a sec and see what ZIO operators I have. Let's see, do I have like a for each par? I don't know if I have it for each par. Maybe I just have forks. Let's see, for each. Let me just quickly. Okay, I guess I can use pn. Okay, let's start with repeat it. Maybe I should. I may in a second. That's the point where I want to implement some other operators there to just help us out. But for now, so let's do. Yeah, I don't really actually want to do. Well, now we can. All right, so let's do ref dot update blank +1. Let's fork that, and let's repeat that. Sure, 1,000 times. Then, because I don't have a good for each par operator right now, just maybe we'll implement that shortly. I think I have a sleep. Let's see. This is also like a good exercise. I don't know if I do have a sleep operator. Maybe I should implement that. All right, I'm going to do it. I'm going to, at least to get us started here, I'm going to do it the old-fashioned way. So I'm going to do. And this really should be running the block controller. I mean, really, we should just use ZIO.sleep, but maybe we'll implement that in a second. And then I'll do ref.get. And let's see what I have here. Right, I'll call this ref example. And then I'll do ref example.unsafe unsync. Should be able to run this now. Oh, and I needed to actually get that. Let's see if we have feedback. No, we don't have feedback. So we'll do value and ref.get. And print out the value. This is why it's nice to use the real ZIO where we have all of our operators. Let's see if we can get it working. Okay, and I guess I should really, if I want this to be 1,000, I should do 999 here, just because that's how many times it's repeating. But aside from that, you can see that as I run this, I'm always getting 1,000 here. And that's reflecting this idea that even though we have all these different threads and fibers that are updating this, none of them are clobbering each other. So we're never seeing a situation where, let's say, fiber A reads 0, and then fiber B reads 0, and then fiber A writes 1, right? Because it said, well, I read 0 and I added 1 to it. And then fiber B also writes 1, right? And this leads us to the wrong answer. We never see that happening, because whenever that would happen, if we go back to our logic in this modify here, we get back to that situation where fiber A read 0, it goes, well, it's able to write 1, this is fine, but then fiber B goes to write 1, and that compare and set fails because it says, hold on, I'm trying to write to 1, but the value that I'm starting with now is 1 instead of 0. I need to go back and do that over again. And so it reads it again, it reads 1, then it does 1 + 1 is 2, and it sets 2, and it gets to the right answer. Let's see if I can illustrate here what happens if I do it the bad way. So if I do it the bad way, I would do ref.get .flatMapN, and then I would do ref.set n +1. And if I've got enough concurrency going on here, this should now give me the wrong answer. And there we go. Look at how many times. So you can see like the difference between this and 1,000 is a measure of basically how many times are we clobbering each other? Are we doing that wrong thing when we do a separate get and set instead of doing them as part of one update operation? All right, anyone have any questions on that? Oh, let's see, could you add a print line to the loop? Oh, okay, yeah, so I think we looked at the race conditions a different way, but yeah. And so in a way, that's it. Like we could go back to ref and we could implement more variants, right? There's like get and set or all sorts of other like permutations of this. But we can really implement them all in terms of this modify operation. And I really like this modify operation because it lets us describe in this one function both how we want to change the state as well as what we want to do based on the state in this one operator here. If we don't have that and I'm working with like just primitive Java atomics, what I find is I often have a situation where I do something like val current state is equal to like ref dot get and update. And I have some function here that has my logic for how I want to transition the state. And then here I need to do something like current state match. And here I have my logic for what I want to do based on the state. Right, so you could imagine this is like, well, decrement the number of active workers by 1. And this is like, well, if the number of active workers is 0, then now call this other thing. And it's much nicer to be able to do this all in one block than to kind of have these like 2 separate ones every time. Let me maybe just show you one other pattern, and then we'll go on to the promise. So one other thing that I like to do sometimes is, so you'll notice one of the little bit of limitations of this ref is that we can't do workflows inside this modify operation. So this is supposed to just be a function that returns a value. It's not supposed to be doing like print lines or writing the database or anything like that. Because again, one, this is supposed to be very fast, right? We don't want something that's going to take too long because if there's someone else modifies under us, we're going to have to retry. So if this took a long time, then we really might be just having to retry over and over again. But also, this might get executed an arbitrary number of times, right? Every time we go through this loop, we're going to call f. And so if f is just like decrementing a number, then it's fine. If we started with the wrong number, we'll just get a new number and we'll decrement that number. But if this was like making a network call, then we might end up making 100 network calls when we're supposed to only make 1 network call. If you really need to do workflows in your modify in this function, there is something in the actual ZIO called a ref.synchronized that basically uses a semaphore instead of using this loop to let you do that. But the vast majority of time, you don't need to do that. You can just return the workflow you want to do as this B value. So let me see if I can give us a little example of this. So let's say that now this ref is going to start out as like 1,000. And now this represents kind of pieces of work that need to be done. And so now, let me say I use this modify. And so this is going to give me this n. And so maybe I'll call this old value just to be really explicit. And so one thing I could say is, okay, well, the new value is just the old value minus 1, right? One of these people completed their work, so I'm just going to decrement that. But then I also want to do some workflow. Let's say I want to do val workflow is equal to, if new value is equal to 0, let's say ZIO.succeed, print line, all done. And otherwise, don't do anything. So then what I could do is modify. I can just return that workflow I want to do and the new value. So now this whole thing is going to return a workflow. And then I think I have flat and defined. Let's see if I have flat and defined. Maybe I don't have flat and defined. Okay, I don't have flat and defined. So that's, we can, okay, this will be a good opportunity for us to be more explicit here. So I'm going to return this workflow. So now my B is a ZIO. And then I can run my workflow. So let's try running this. and sorry, I need to dot repeat n. And, and I need to fork these so that I'm actually doing this in parallel. So this is interesting. And now, oops, let's see. Okay, so all right, let me actually implement flatten here for a second. So I'm going to go back to ZIO. And I've already got flat map. And I'm just going to implement flatten. I think, yeah. And so flatten, I'm going to require this evidence that the output type of the original ZIO is a ZIO itself. So basically what this flatten is going to do is it's going to take me from a ZIO, ZIO, EA to a ZIO, EA. And it's actually really simple. It's just flat map with essentially the identity function. I'm just using this evidence as a function here to prove to the Scala compiler that this thing really is of the right type. So now let me go back to my ref example here. And now I'll flatten this. Now let me run this. And so you'll see, even though we said, well, you're not allowed to do ZIO workflows within the modify, I can still do a workflow based on the modify operation. And so this is, I would say, a pretty common pattern where you update something and then you both update the state and you decide some other work you want to do based on that. So like here, I just printed all done if I was done and otherwise I didn't do anything, but like I could also, and one thing you'll notice here is like the values can be a little out of order of when these things get printed, but it is the one that's the last one that did the all done. So that's kind of a nice, nice pattern for working with refs. But that's probably enough of me waxing poetic about refs. I'm going to just check in here, and then we will move on to promises. Okay, so let's look at promises. Oh, all right, let's see, Juan is typing. So I'm going to give Juan a second here. So Juan is asking, why do they get printed in the wrong order? And so the answer is what we're returning here is a workflow here, right? So we have 1,000 fibers, or let's just imagine, let's just simplify this to say we have like 3 fibers. So we have, right, fiber A, fiber B, fiber C. And so they're all going to be going ahead. And let's say that fiber A reduces the value to 2, fiber B reduces the value to 1, fiber B reduces the value to 0. So based on that, they're all going to decide what the work is that they need to do. So now 0 knows that it needs to print all done, and this needs to know to print still 1 left to do, and this needs to know to print still 2 left to do. But these are all still running on separate fibers. So there's no guarantee of the ordering between these different workflows running. We have a guarantee that this last fiber, which is the one that was that did this, was the last one to decrement this, but we don't have a guarantee between when these things are going. But most of the time, that won't actually matter for us, because what we'll actually have is, let's say this one is going to do some work, And then it's going to decrement it, right? This one's going to, excuse me, not to, but do some work. This one's going to do some work. And this one's going to do some work. And so in this world, the fact that this one set it to 0 means that everyone has already finished doing their work. And so, like, I mean, this might be a good reason I just added these kind of for a little bit of a silly example. But what we would have here is we would have a guarantee that all done is not going to be run until everyone has finished doing their work. Does that make sense, one? Okay, I'm not saying you're typing, so oh, okay, I'm gonna give you a second here. More or less, okay, I'll take that as victory for now. Okay, so let's go to promise here, and maybe I can always flip back there if we need to. But so the other key concurrency primitive in ZIO is this thing called a promise. And so a promise is a little like the like a Java promise in a way, or if you've worked with Scala features, a little bit like that. But it essentially gives us a way to wait for a value to be set. And so you'll notice, like the ref, it doesn't have any concept of waiting, right? It's just going to get some value, and maybe it'll loop briefly just if there's a conflicting update. But otherwise, it's just going to give you the value, and you're going to do something based on it. So, like in our ref example, none of these fibers were waiting on each other. They were all just doing exactly what they were going to do. And just based on this information they exchanged with each other, they might do something a little bit differently based on that. But no one was ever pausing, waiting for another. And oftentimes that can be a really good pattern, because that's an efficient way of doing things. If you don't wait, you just change what you do based on what other people have already done. But sometimes we really do need to wait for a condition. And so you can think of ref as like really good for this, like updating, communicating about state, but it has like no concept of waiting. And so promise is going to be all about this, this idea of waiting. And so again, we may have some like a little bit more specialized operators, but the most primitive one is going to be this one called await. And then we'll have one called complete. And so await says, wait for a value to be set and then return it. And complete is going to say, set a value. And so another way to think about this promise is it's like a box that contains either an E or an A, and can be set exactly once. So the box is either empty or it's full with an E or an A. And then given those two, we could have some convenience operators. We could have one that says, well, if I want to complete it with a success, then I can just complete it with ZIO succeed A. And if I want to complete it with a failure, I can just complete it with fail here. And oh yeah, both of these, I don't need the type parameter. Okay. And so this one's going to take a little bit more work, just because this is going to be a little bit more of a homegrown thing versus we're not going to be able to lean so heavily on like the Java ref for it. But a way we can start to think about it is we can think about the different states that we have here. So we could have something like a sealed trait state. And so I think if we just kind of take our discussion here, we can kind of see that there are two states basically. So we could call it maybe empty, and I think I will need to give these some type parameters here. But so if it's empty, then it's basically, it doesn't have a value inside of it, but it has some people who are waiting for that value. So we could think of those as like callbacks. And each of these we could think of as like, I think a basic so each of these is someone who's interested in the result of this promise and is going to do something with it. We don't know what they're going to do with it, but they're going to do something with it. And then and so that will extend state. And then the other possibility is that it's full. And so then if we had that, we could start to implement our little make method here. And so the basic signature of this is going to look similar to the one we did for ref, except that there's no initial value, right? When we make the promise, it's just empty here. So we're not going to provide an initial value. And so what that usually means, if you've like worked with a ZIO promise, is usually when you make the promise, you just specify the type parameters, just because otherwise there's not a way that the compiler is going to know what the type of this promise is supposed to be. I think I'll start off by just giving myself a succeed block here. I'm sure we'll ultimately need that. And so we're going to create a new promise. And I think based on what I did before, I'm going to have these two primitive methods that I need to implement. And complete. And we might also change this complete to return like a Boolean to say whether we were the ones who filled the box or if it was already filled. But I think maybe right now I'll just leave it as you know, for simplicity here. Okay, so we've got this state, and we need this state to be potentially interacted with between these different fibers that are working with this, because one fiber is going to be completeness, one fiber is not going to be. So we're actually going to want either a ref or an atomic reference here. Maybe I'll start by using a ref. We may find it's will be a little bit convenient to switch back, but let me start with this for simplicity. So we might say, okay, well, I'm going to start with a state, and my initial state is going to be the box is not full yet. And initially, there's no one who's interested in the value of this promise. And so let's think about what we need to do in these two different operators based on this. So in await, we could say ref.modify, right? And so we're going to start with the state. And we're going to want to return two things based on it, right? If we're using modify, we're going to want to return a new state. And we're going to want to return an actual result of this. So the state, there are two possibilities, right? We're either empty or full. So I could change this into a pattern match. So I could say case empty callbacks, case full ZIO. And so here's where we're going to be able to take advantage of one of the other ZIO operators we have. At least I hope we implemented this. Let me go here. Yeah, so look at this operator we have. So this is the async operator that we can use to basically import some asynchronous code into ZIO. And so the async operator is what's going to let us kind of do this concept of waiting here. And so what I'm going to do, just going to quickly check in on our comments, make sure we're good. Okay. So I can use this async operator here. And so let me make this ZIO.async EA. And this is now going to give me a callback. So if I hover over this, let's see if I can get some. Oh, hold on. Wait a second. Okay, I put that in the completely wrong place because I went to the wrong file here. So let me undo that and let me go to the file on promise. That was very silly of me. All right, so here I can do ZIO.async. Okay. So I'm going to do an asynchronous call, and I'm going to look at this ref. And I think the only thing I'm going to need to do here is I think I will go back to using the atomic reference only because that's going to let me return unit versus ZIO here. So I think I'll change this. So I'm going to make this ZIO succeed instead. And then I'll do val state equal new current atomic reference state empty. Okay, so now, so now we can do this asynchronous operation. And I am going to do a little bit of my trick here because I'm using the lower level one. So I'm going to do val current state is equal to state dot get and update. And so I've got these two different possibilities for the state. So if the state's already full, then I can just call the callback with the ZIO, I believe. Let's see. Oh, sorry. This is, see, I'm confusing the updating the state versus doing something based on a state. So we're going to do something based on the state in one sec down here. Okay, so here, we're going to say, if the box is already full with a value, then we don't need to change the state at all. The box is still already full with a value. If the box is empty with some people who are interested in the results, then we need to add ourselves as another person who's interested in the results. And then, based on that same state, we'll look at it. And if it's empty with some callbacks, then we don't need to do anything with it because we already registered ourselves up here. And if it's full with a ZIO, then we just need to call ourselves back with the ZIO. So you can see this is like a little bit low level, but really a lot of this hard part is getting taken care of for us by the ZIO.async here. And then we can do the same thing down here with complete, except here, I don't think we're even going to need the async here. So I think here, we could just do ZIO.succeed. And we could say, do the same pattern. So we'll do the state.get an update. And if it's empty, with some callbacks, then we're going to set it to being full with our value. Empty. And if it's full with a value, then we're just going to leave it alone. We're not going to do anything. Again, we might change this to Boolean and return the Boolean to reflect that, but we're not going to do that at least yet. And then we're going to look at a state. And and if there were some callbacks here, then we're going to need to call them back. We'll do that in a sec. And if it was already completed, then there's nothing for us to do here. So here, I'll just make this unit. And then here, I will call each of the callbacks. Because this is just a function from ZIO to unit. So for each of them, I'll give them their ZIO. And yeah, a lot of times the inference is not as good there. Let me see if I can get away with that one. Yeah, I can get away with that one at least. But it definitely, the asyncs can be a little bit mind-bendy, but I just think about it as like the async just gives you this callback thing, and you just need to make sure that somewhere, someone actually calls the callback. Okay, so let's see if we can do an example of this, and then we're past the hour mark, so I think that'll probably be a good wrapping up point. Oh, not promise, but promised example. Okay. And so let's do example. Things out. Okay, and so promised example, we'll do something like we're going to make a promise. And then let's create someone that's going to do something with it. So let's do like promise.await, .flatmap, and ZIO.succeed, print line, Zimmer got, unit down here. And then I'm going to make us, and again, I'm going to do it the bad way right now, just haven't implemented the non-blocking sleep. But I'm going to make sure we wait a little while to make sure that like this one's just had a chance to, I just want to make sure we simulate kind of the scenario of like the promise isn't completed yet, because otherwise it's kind of the easy case. And then we're going to have someone that completes the promise. And let's see, I'm going to want to fork this. I'll call this fiber, not Fuber. And then I will join the fiber. Okay, and let's see if we've implemented this correctly. So we found this example. And consumer got 42. And there we go. So I think you can see here, I mean, it wasn't completely trivial, but there's actually like, I don't think it really qualifies as rocket science here, right? I mean, especially the ref, we just essentially wrapped the atomic reference. We did a little bit of compare and swapping here. And then in the promise, we really got most of the hard stuff done for us with this ZIO.async. And then the only bit that was slightly tricky beyond that was just using the Java atomic reference here and thinking about having these like empty and full states. But these two things are like probably the key concurrency primitives in a lot of these frameworks. And so hopefully you can see here that like, it's actually not magic. You can, I mean, we can implement it ourselves pretty easily, even with this like toy framework, and especially with the real framework. If you decided for some reason, you know, like ZIO's promise and you want to create your own, you could use the real ZIO.async here and you could use it to implement your own promise just like this. So hopefully this has been good and demystifying. But maybe I'll give us a minute here for questions and then we can break. All right, awesome. Well, thanks so much, everyone, and have a fantastic weekend. I think it's a long weekend for a decent number of folks in the world, at least Europe and US. So enjoy yourselves. All right, bye, everyone.